Okay, so now it is Wednesday, 3/21, and this is the notes for 7.1, part 2. And it's my hope that we'll maybe finish this today. And number 4 is solve the system of equations, which is negative x plus y equals 4, and x squared plus y equals 3. And so just a reminder, that's a linear and a nonlinear equation. And so the first thing that we're going to do is take the linear equation, solve it for y, so that when we put that expression in the bottom one, we will have we'll have all x's and it'll be an x squared. So our first step is to take negative x plus y equals 4. So y equals x plus 4. And then steps 2 and 3 are to take that x squared plus this stuff equals 3, and this stuff is x plus 4. So then we get x squared plus x plus 4, subtract 3 from both sides, minus 3 equals 0. We get x squared plus x plus 1 equals 0. I gave everybody who was here a few minutes to work on this, and what they discovered is that there is no number that works to multiply by itself to be equal to 1 and also add to be 1. So you can't factor it. Your fallback is the quadratic formula. So x equals negative b. And so here a is 1, b is 1, and c is 1. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so then we get x equals negative 1 plus or minus the square root of 1 squared is 1, 1 minus 4 is negative 3 over 2. And this is not real. And so if that's not real, remember the solution to this is where these two things intersect. It's a line and a curve. And so if it's a no real solution, then that means they don't intersect. And oops, so we'll write no real solution. The next thing I have for you to do is on a little handout. And so if you are gone, you can look at that next slide and pause it and just try to figure these things out. And then the slide after that is going to have the solutions on it. And so here is the question that I'd like you to answer. And the way that I answered this when I answer it myself is the question is, how many possible solutions are there for the following systems, and show graphically. So, you know, for instance, two lines, linear, I just drew a picture of two lines intersecting, but what else could happen? So take a minute and try to draw yourself, you know, if you want to use the space below there, a little picture that's showing, in your opinion, of what you think all the possible outcomes are. And I am not sure where my recording box is. Oh, there it is. I am going to pause this for a moment, and then when I come back on, we'll go over the answers. Okay, let's take a minute and kind of see what we got for these. Just a nice little exercise for you. So if there's two linear equations, they can be parallel, so there's no solution. They can intersect, so there's one solution. They could be the same line, so I'll just make it thicker, and have an infinite number of solutions. For two lines. If it's linear and quadratic, we could have the quadratic equation like that and maybe the line like that, so it can have 0. We can have the quadratic like that and the line like that so that there's one solution. We could have the quadratic like that and the line like that so there's two solutions when we have a linear and a quadratic. And then a linear and cubic is that we can have that cubic equation. I'll just kind of do it like that for now. And it could have one solution, and it could hit there twice or 3 times. There's 3 times, 1, 2, 3. And It could hit twice if it kind of goes like this, where it hits the top of that and then maybe just goes through there as well. So it could have two as well. Then linear in a circle, circle in a line could have 0, circle in a line could have 2, circle in a line could have 1. Pretend that is 1. Quadratic, quadratic, we could have two quadratics like that, hopefully those have 0. A quadratic like this and a quadratic like that has 2. If you're just, exactly there, they could have 1. And since quadratics are the same type of function, they could have also be the same quadratic and just one a multiple of the other and have an infinite number of solutions. Did I miss anything, do you think? Did I miss anything as I went through that? But just a good little reminder, because I guess in the past, most of the time you've done linear systems of equations, so things like to look for and kind of things to know about, so you have expectations for what might be happening there. And that was if I just decided to show it. So now we're going to look at the graphical approach to finding solutions. In the past, when we've done linear equations, I should turn the light out. When we've done linear systems of equations, always linear, we have, we've really said that the graphical approach wasn't always the best because we wouldn't maybe get a grid point, do you know what I mean? And so like elimination or one of those others sometimes is better. But we will find that sometimes graphing it might be a good idea because if they're non-linear, it can give us a visual idea, just like we looked at, of where those zeros might be. So a system of two unknowns can have one solution, more than one solution, or no solution. And so using graphing, we can get kind of some insight about where that is because we're looking for a point of intersection. And that's what we're doing when we look at these graphically. And then, so, two lines, they intersect once there. The parabola and the line intersect twice. The parabola and that other line have no points of intersection. And we just kind of went through a bunch of those to kind of see what can happen. So our next one is to graph a nonlinear, and I think the other one is linear. And so we've stepped our game up a little bit because look at one of them. It's a logarithm. And so that's going to be, just a little bit more difficult. You maybe want to use a piece of graph paper or your notebook paper. I prefer graph paper for this. And we'll graph y equals the ln of x first as we go through this. And the way that I would graph that is just a little reminder that ln of x equals y. So this is e to the y equals x. And then personally, I would make a table of x, y values. I would pick y values and then figure out what e is to that power and then kind of graph those. So -1, 0, 1, and 2 will be my problems. I can do a few of these without having a calculator. So e to the 0, anything to the 0 is 1. E to the 1 is about 2.7. So somebody tell me what e to the -1 is. And I only want one decimal place because let's face it, I don't have big grids here. 0.4. And e to the 2, 7.4. So I think I can kind of graph those as well enough. And 7.4, I'm going to leave the axes like this, oops, as I go through this one. And so then I'm going to just plot these points. So keep in mind, 0.4 is about, not quite halfway there, and then -1. So there's my kind of point for that first one. 1, 0, right there. 2.7, here's 2, 2.7, comma 1, might be about there. And 1, 2, 3, 4, 5, 6, 7.4, and comma 2. And so then this, I am going to try that again. This one should go like that. Ooh, not bad, in my own personal opinion. So we've got that graph of that function, and then our other one is x plus y equals 1. That is linear, so I would get y alone, so y equals negative x plus 1. The slope, m, is negative 1. The y-intercept is positive 1, equal b is, oh, I'll rewrite that just a little bit there. The y-intercept b is positive 1. And so it's pretty easy for me to graph that. Here I'm at positive 1 for the y-intercept. Slope is negative 1, so it's going to go like that. When I do these at the smartboard, because I'm going to use that line drawer, it's easiest for me if I put in a lot of points. You certainly probably would not do that, but that just makes it easier for my own self as I go through that. And then graphically, this one, boy, let me, there we go. This is going to be about as good. Graphically, I can even see for this one the point of intersection. So our point of intersection is right there at 1, 0 is the solution or that point of intersection. Solution. And sometimes we'll use that just to give ourselves kind of an idea of where that solution might be as we go through this. Then the next section here is on, or the next part of this section is just some applications. And let me just see this. Shows the benefit of the graphical approach. Oh yes, because if you did solve and then put that logarithm in, you get x plus the ln of x equals 1, and that's a little more difficult to solve using kind of standard algebraic techniques. So then applications is the next thing. And so we're going to start with a very simple kind of economic problem, I guess, is the closest I could say for that. And so then for this one, just a couple of reminders. The total cost of producing X units of product typically has two components, an initial cost and a cost per unit. And then when enough of those units have been sold so that the total revenue equals costs, the sales are said to have reached a break-even point. Just give me a head nod. Is everybody familiar with a break-even point? Yes. Okay. So just a little reminder of that. And you can find the break-even point that corresponds to the point of intersection of the cost and revenue curves as we look at that. So here's our problem that we're going to look at, and I'll just kind of write some of the information. So this company invests $300,000. That's their investment, and invested in, we'll say supplies or something, in equipment to produce a new line of athletic wear. Each pair of shoe costs $5 to produce. So it costs $5 to produce one pair of shoes. So those are going to be our costs, and that can give us a cost function. This is our costs, our C, and we can get a y equals mx plus b. It's just linear in this case. To produce these, it'll cost $5 per pair of shoes, plus that $300,000 for supplies. I think I have enough zeros there, a little messy. And then when we're selling these shoes, they just sell for $60. So we'll sell the shoes for $60. And that's really all it tells us there. So that's going to be our revenue, and R for revenue. And that's just going to be Y equals, it's for $60 a pair, I should have added. So that's going to be 60x. And then we want our break even. How many pairs of shoes must the company sell to break even? And so that's just when profit, revenue, and costs are the same. And oops, so I'm just going to remind us that profit equals revenue minus costs. Just a little reminder to you of that. And then break even is when revenue is equal to costs. And so we can just set those two equations equal to each other. 60x equals 5x plus 300,000. And when we subtract 5, we'll get 55x equals 300,000. And then we're going to divide by 55. That I don't know it is on the top of my head. So what is 300,000 divided by 55? And when you're getting that answer, I want it to the nearest whole number because, like one less pair would not have broken even, and so we'll just go a little over that. What is it? 5,455. And so we have to sell 5,455 pairs of shoes to break even. And so that is just a little problem that we wanted to go over as we look at that. I have one more application problem like that, and let's kind of look at that for a moment. And oh, that I think we already said. Okay, so this one's a little small on the slide, but we have the two equations here. The weekly ticket sales for a new comedy movie is for a new comedy movie decreased each week. And at the same time, the weekly ticket sales for a new drama movie increased each week. And models of the approximate weekly ticket sales S in millions of dollars for the movies are S equals 60 minus 8x and S equals 10 plus 4.5x. And do we know which one is decreasing and increasing? Yes, and how do we know which one is increasing and decreasing? Right. The subtracted one is decreasing, the added one is increasing. Where X represents the number of weeks each movie is in the theaters, with X equals 0 corresponding to opening weekend. So it looks like that opening weekend, when X is 0, S was 60, and then S was 10 for each of those respective movies. After how many weeks will the ticket sales for the two movies be equal? So for 7, our system of equations is S equals 60 minus 8x, and S equals 10 plus 4.5x. And so again, we're solving this system really using substitution, where we're replacing one of the S's with the other rule there. And so 10 plus 4.5x equals 60 minus 8x. And when we add 8x, we get maybe 12.5x. And we subtract 10, we get equals 50. And what is x equal to? 4. And so notice I'm also writing kind of a answer that goes with these. So in 4 weeks, the ticket sales will be equal. The ticket sales will be equal. Ooh, maybe I should write that as a word too. Equal. As a little sentence there. Oops. And So that is everything for this section. And that took me 19 minutes. So we're done with 7.1. And then the homework check for 7.1 will be next Tuesday. Tomorrow we'll do some notes for 7.2. Those of you who are here just have some work time for 7.1. And there are books in the back. And if you have other things to work on, you may as well.